This is the final module. So let's get started. So we've seen a contingency table. A contingency table is using two categorical variables. This is key to this chapter. In this chapter, we are going to use two categorical variables, and we are going to use a test of independence to determine if there is significant association. Now, I want you to think about this. We are trying to find a significant association. This should tell you the null and the alternative right there if we are trying to find a significant association. We wouldn't start out believing one is there. The null is what you start out with. The alternative is what you try to find evidence for. So, a little bit of knowledge coming our way right there. The alternative is going to deal with finding a significant association. We've seen this data before. In Chapter 2, we saw the Titanic data, and if anyone told me if they hopped in a time travel machine and they went on the Titanic and they wanted to be in the crew, well, I've had people tell me that. And they're like, I'd love to party, be in the crew. And I'm like, well, it'd be a fun ride for a while, maybe if they're... I don't think it was like the Titanic where they were dancing and partying, the movie Titanic. But we can see that there's a clear association between what happened on the Titanic, where first class had a much higher chance of surviving over crew. We can see here, unfortunately, 3/4 of crew, or well beyond 3/4, tragically died, and around 2/3 survived and 1/3 died. Here, if you see just by, there's 325 people, and if you kind of do a little round and you have 2, 1, 3, that all rounds to 2/3. I'm just doing some very big rounding. 2/3 survived here. If you round this to 2, 6, 8, that's some really heavy rounding, but still it's only 1/4, 1/8, or 2/8, which goes to 1/4. So there's some sort of association going on here, and I think we'd agree. There's an association between which class you were on in the Titanic and your survival. We would all agree with that. So what we have here is the null and alternative. Yay! Nulls and alternatives. We love them. Because the null is what you would believe without any evidence. So we would say that the row and the column are independent of each other. That is what we just start out believing. The row and the column are independent. In other words, that class is independent of survival. This just has no effect on it. Class is independent of survival. You can also say class has no association with survival. There's no association between class and survival. Class is not related to survival. Things like that. A lot of times, since this is a test of independence, we will say class is independent of survival. So the opposite of independent is not independent. So if we say it's not independent, like, if we were to say your letter grade on the test is not independent of whether you studied the night before. And think about that. Letter grade on the test is categorical. And studying the night before is categorical also. These are yes/no questions, such as, did you study the night before? What was your letter grade? A, B, C, D, F. So since it's categorical, we could probably see if they are independent or not independent. And my guess would be your letter grade is not independent of whether you study. When we say your letter grade is not independent, we are saying your letter grade is dependent. If you think about the wording, not independent means dependent. So it might make more sense to you when we say it in the fashion, your letter grade on the test is dependent on studying the night before. Or for this one, if we were to say, your survival on the Titanic is dependent on your class. So we have conditions. Love the conditions. So I always start out with condition 1, condition 2. And they call them assumptions, but I still call them conditions. So we have the randomization condition. Oh, it's an assumption. That's a condition. That's always great. And a condition, that's an assumption. So we have the randomization condition, condition 1. 10% condition, condition 2. And why do I always say condition 1, condition 2? Because these are the first two conditions on every test and every conference interval we've been doing lately. So it's kind of gets it in your mind to say condition 1, randomization, condition 2, 10%. Next, we're going to have the count data condition. Count data comes about when we have categorical variables. That's how we get count data. Going back here, we can see this is count data. 203 represents 203 people who were in first class and who stayed alive on the Titanic. So the final condition we have is with the expected cell counts. And I just call it the expected cell count condition. It's a sample size assumption, expected cell count frequency condition. I just call it expected cell counts. It's fine by me. So with the expected cell count condition, we want there to be at least 5 individuals for the expected cell count. So what is the expected cell count? The expected cell count is how many we expect there to be. And you can get these numbers. Let's go back to our Titanic example. You can get these numbers by doing row total times column total over grand total. And so let's take a look at this right here. If we were to get the expected cell count for a live first class, we would have the row total times the column total over the grand total. Now I want you to take a look at this 104.99 and how we got it. If you take a look, we just line everything up. Everything is lined up with the row and the column. You circle the row total, you circle the column total, and you divide by the grand total. Row total is going to times by column total. Always use this pattern right here to solve for your answers on expected cell count. So you can see they go into greater detail right here. You're free to read over this, but remember, it's just row total times column total over grand total. That is what we are doing right here to get the expected cell count. Now we need to find a difference. So the difference is going to tell us how odd things are. We have an amount we observed, and we have an amount we expected. When we do this, we would get 0 if we just added them all up, if we added up all the differences. But what about if we square the differences? Squaring the differences makes them all positive. Now that all the differences are squared, they won't add up to 0 because there are no longer any negative differences. But then we need to do it to relative size. Because, and I want you to think about this example with the bottom equation. The reason we standardize by expected is because of this. I have person A, and person A is going to get paid $100 for a day's worth of work. When they come to get paid, I say to them, great job, I'm giving you $200. Well, they expected $100 and they observed $200. We can go down here to this equation. They expected 100 and they observed 200. That's a difference of 100, and when you square it, a difference of 100 squared is 10,000. So with that in mind right here, 10,000 divided by 100 is 100. So we have 100 squared over 100, and that's 100. That is our standardized difference right there. But what about if I have a person who I say to them, I'll pay you $20,000. And so they're thinking, wow, this Brian Stevens is a nice guy. He's going to pay me $20,000, and basically going to pay me a lot more when I come in. So they expect $20,000. And when they come in, I give them $20,100. They observe $20,100. So once again, we have 20,100 minus 20,000. It's a difference of 100. 100 squared is 10,000. 10,000 over 20,000, because now they expected 20,000, is only 1/2. So for a whole year's worth of work, this person I said pay them $20,000. They thought, oh, I'm going to get like 40,000. He doubles it. No, they only got the 100 more. In each example here, the person got 100 more. But the person who expected 100 was a lot more surprised to get 200. To them, that difference of 100 was huge. They're like, whoa, $200? I only expected 100. But the person who expected 20,000, that difference of 100 wasn't that big. Think about it. The standardized difference tells you how odd it is. Because in the first example, the standardized difference solved out to 100, which is much bigger than 1/2 in the second example. The standardized difference, or what we will call the cell chi-squared, tells you how odd each cell is. So we can solve this formula right here for every cell. Every cell will have an observed, also known as the count, and we'll have an expected. So if we get it for every cell, why not add them all up? And this tells us how odd all the cells are. And when you think about this, according to the null, if there is no relationship, we would expect the observed to equal the expected. The null is what we expect, and we observe something. So if the observed equals the expected for all of these, this top part would solve out to 0. And where would you fall on the chi-squared? 0. If you add up all zeros, because every observed equals every expected, and frankly it wouldn't matter what we divide by then, because if all observed equals all expected, this equals 0. 0 squared is 0. 0 divided by anything is 0. Add up a bunch of zeros, and you get 0. So this is the null kind of value. The null, what we expect to get, would be for chi-squared to equal 0. Which is weird because, wait, you're like, well, 0 is at the center of the distribution. Not this time. The chi-squared only has positive values. Remember, we are adding up squared values. The chi-squared only has positive values. 0 is the lowest value on the distribution, and we will be doing a right-tailed test for this. But we don't know which chi-squared we're using yet. Once again, we have degrees of freedom. The degrees of freedom here are going to be rows minus 1 times columns minus 1. This means if you have a 2 by 2, it turns into a 1 by 1. 2 by 2 turns into 1 by 1. And with that in mind, it's 1 degree of freedom. How about a 4 by 4? If we have 4 rows and 4 columns, that turns into a 3 by 3. 3 by 3 is 9. Do you see what I'm doing here? What if we have an 11 by 2? That turns into a 10 by 1. And that would be 10 degrees of freedom. Let's look at a visual example right now. Go back to our Titanic, and what do we have? We have a 2 by 4. A 2 by 4 turns into a 1 by 3. Make sure to not use the total columns. Make sure to not use the total columns. This is a 2 by 4, which turns into a 1 by 3. One thing I like to do is I like to shade in an L. If you draw in an L, you're actually deleting off 1 row and 1 column. And then you can see that it is a 1 by 3 inside. This would mean this distribution right here comes from a chi-squared, or when we test it, comes from a chi-squared with 3 degrees of freedom. We have to use the chi-squared to find the probability of our results or results more extreme given that the null is true. Once again, we would expect, according to the null, to get a chi-squared of 0. So let's go ahead and take a look at a chi-squared applet. These are the Matt Bogner applets. They're if you type in Iowa, applet, anything, chi-squared applet, you will get these applets. He's done a great job with these. Our Titanic one was a chi-squared with 3 degrees of freedom. And this is what it looks like right here. We could put in our value of chi-squared right here under the x. And maybe we got a value of 20, which is way off the grid. Value of 5 you can actually observe, and you shade to the right. So the chi-squared, you need to define what chi-squared it is, which degree of freedom it has, and then you need to define your chi-squared value, and then you can get the probability. So as we can see right here, we can change this to 8, and we can see how the value moves, and we get a smaller and smaller p-value. At a chi-squared of 8, we could reject the null, and this is on a chi-squared with 3 degrees of freedom. Chi-squared with 3 degrees of freedom, and this x right here is your chi-squared value. So they have another chi-squared applet right here. There's tons of chi-squared applets. Also the stat distributions page, if you type that in as one word, stat distributions chi-squared. They have a good applet that they use. Excellent stuff right there. What we're going to see is that large chi-square values give us more evidence to reject the null. It means a greater deviation from the null. They will give us small p-values, and we saw that before. The larger the chi-squared, the smaller the p-value. As we stated before, if the chi-squared is large enough, we'll be able to reject the null. We're not going to make confidence intervals from this, at least in this class. What we're noticing here is that the chi-squared is going to tell us how much the observed and the expecteds don't match. And it can't be too small or negative. There is no too little of a match with the observed and the expected, because if they match up perfectly, it's not too small of a match. They can only deviate too much. That's why it's a right-tailed test. It also can't be negative because we're just looking at the squared deviations. So now we have an example here with the type of car and whether or not it needs regular maintenance or regular and unexpected maintenance. So what would you assume to start? That there's no association or the two are independent. That maintenance experience and type of car are independent of each other. What about for your alternative? That maintenance experience and type of car is not independent. You see it uses my association word. I love that. The maintenance is associated with type of car. And the null would be that maintenance is not associated. You have to think carefully if you put the not in, because you're basically starting out by saying that there's no relationship. So maintenance has no relationship to type of car you have. The alternative would be that maintenance has a relationship to the type of car you have. Here we see all the math, and I encourage you to check your skills right here. I encourage you to go through and see if you can find the expected value. We see the mathematics right here, 66 times 146 over 200. Remember, always circle your values and then divide by. If you line it up right there. Circle the values, put your underline, and then divide by the grand total. And we see the math right here, and you can check any of your other ones to see if you can get the expected cell counts for each cell. Here we just see the math behind what we have on the previous page. You're free to read over it. It's just showing you that you are just taking the row and the column, timesing them together, and then dividing by the grand total. Once again, the same formula we are doing. Now we need to get the cell chi-squareds. So we have two steps so far. Find the expected, find the cell chi-squared. The cell chi-squared is the observed minus the expected squared over the expected. So you'll notice here we have 42. 42 goes down to there. 48.18 goes to there and there because we're putting it into this formula. Each one of these cells now has this formula in it, and we solve. So which one was the oddest? The oddest one was the Toyota that needed regular and unexpected maintenance. If you notice, Toyota did really well at that. There are very few 12 out of 82, because there's an 82 total Toyotas, and the other ones had fewer cars in it and needed more unexpected maintenance. Toyota was doing really well here, so unexpectedly well, and that's our biggest unexpected right there. So what do we do with all the cell chi-squareds? Remember, step 1, find the expecteds. Step 2, find the cell chi-squareds. And then what do? We take all of them and add them all up. So we add up all of these values right here, these cell chi-squareds, and we get what is called the Pearson. I want to make that clear. This is the Pearson chi-squared test statistic. If you forget, remember the Pearson is your p-value. As long as you don't forget that, the Pearson is your p-value. You'll see two p-values in JUMP, one related to the likelihood test and one related to the Pearson chi-squared test statistic, and this is your p-value. The Pearson is your p-value. I can't make that clear enough. The Pearson is your p-value. You're on my Pearson right now, or you will be, and the Pearson is your p-value in JUMP. So we have to give the degrees of freedom. This is a what by what? It is a 2 by 3, so 2 rows, 3 columns. That makes it a 2 by 3, turns into a 1 by 2. 1 by 2 is 2 degrees of freedom, right there. Here is our chi-squared with 2 degrees of freedom, and we have plotted in the Pearson chi-squared test statistic right here, and you can't but barely see it. So I'm going to go to my applet and see if we can see it a little bit more closely. So I'm going to now change it over to what we have from the problem, 2 and 10.82, I believe it was, and we really can't see it. It is off the curve. The p-value is so incredibly small, we can't see it, and yeah. So with that in mind, this is definitely reject the null. The null was that there is no association between car type and maintenance needed. The alternative is that there is an association between car type and maintenance needed, and we definitely have evidence that there is an association right here. As we said, we reject the null hypothesis, and we probably want to take a look at the Mosaic plot because it's going to make it easier to see. And if you look, what I noticed with the numbers shows up here again, that Toyotas really don't need unexpected maintenance. Toyotas are only needing regular maintenance. And it's not like all of them only need regular maintenance, but it was the most unexpected. Remember, I looked at the largest cell chi-squared to figure that out, and I was like, oh, this is really unexpected right here, because that's what the cell chi-squared is giving us. The cell chi-squared is the standardized how unexpected it was, and that's very unexpected. There's the percentages right here. We can always put in the row percentages just to see what percent, and only 14.6% of Toyotas needed unexpected maintenance. And that's a big difference because these other twos, Ford and Chevy, they're about on par with each other, about the same amount of unexpected maintenance. As we said, the cell chi-squared is showing us how odd it is, and that's an odd cell over there. So when we have X and Y in jump, sometimes it can look nicer to flip them in jump. It really doesn't matter which one we put in as X or Y. The math will solve out the same, but it's just in a visual thing. So don't worry about putting X or Y or X for jump, because it's going to be the same. In Mosaic plots, it'll give you the same output. Now, I want to mention this. If you're doing the project and watching this, if you have a categorical X and a quantitative Y, this is not this chapter, but if you have a categorical X and a quantitative Y, you will be analyzing means, because it's going to create groups with your categories on the X, and the quantitative Y is what you're analyzing, the means. But if you have a quantitative X and a categorical Y, you will get logistic regression. And we don't do logistic regression in this class. It's another class, but it's switching your X and Y in that instance will not get you the same output. This is kind of like a regression, where if you switch X and Y in regression, while you still might want to be using a certain X to explain a Y, you'll still get the same regression output. It'll be flipped a little bit, as the Mosaic plots will be flipped, but you'll still get the same sort of idea from it. You'll get the same R-squareds. You'll get a different line with a different slope, but that's the great thing about Mosaic plots is there's no intercept, there's no slope. You're just going to get cell chi-squareds and all that, and all the math will work out exactly the same in Mosaic plots. So Mosaic plots are the one where switching X and Y will just create a visual difference. So here we have the switch, and you notice it's just looking at it in a different way, and you can really see that the percent that needed unexpected maintenance, well, Toyota was the smaller one right here. So when the p-value is small, does this mean that one causes the other? No, it does not at all. It could be that maybe Toyota gives their people regular checkups. Maybe we went and got info from a Toyota place that says we'll give you a free checkup every 30,000 miles. And people are including that in their regular maintenance, which it is. I'd say it's regular maintenance. But they're getting the people in there, and they're probably heading off any problems. So it's not the Toyota car that's doing it, if this is what's happening. It's probably, and I'm not saying it is, but it's more likely to be that Toyota gave out some sort of, come in every 30,000 miles and we'll give you a free checkup. And they're calling it regular maintenance right there, where the other car companies aren't doing that. Not saying Toyota does that, but it's just, we can't say having a Toyota causes people not to get unexpected maintenance. It could have been some other lurking variable. Lurking variables come back once again. We can't say one variable causes another unless we do an experiment. So we have here fish and prostate cancer. We always have such fun topics, especially in this chapter. The Titanic, your car breaking down, and fish and prostate cancer. Nice. So here's our data. We have our conditions to check. Is it categorical? Yes, it is. That's count data. Did we randomly select these people? Somewhere along here, we need to see the word random. And if we had written the problem a little bit better, we would have probably put random in there. But as long as the problem says random, it's random. So we would need that in the problem. 10%. Is this less than 10% of all people who eat fish and or get prostate cancer? And I'd say yes. This is, considering it's yes, no prostate cancer, it's all people. And fish eaters, we should be good. 6,272 means 62,720 people must, be in this population, which I think we're good. Expected cell count. Now here's the one people have the hardest time checking. We need all the expected cell counts to check it. So we're missing one right here. Expected cell count is, as you notice, lined up with expected right here, and that's the expected. Always look at this table to see what value the orders are in. We have count at the top, which is just our observed. We have expected second, and we have cell chi-squared third. Now we can actually check the expected cell count right now with this table, because think about this: the equation is always row total times column total over grand total. Grand total never changes. What does change is the row and the column. So why not take the smallest row right here and the smallest column. Now, I'm not doing this because of the 14. That's just happenstance. I'm taking the smallest row and the smallest column, and it lines up to right here. And this has an expected count of 9.2. Smallest row times smallest column over grand total is your smallest expected cell count. If your smallest is greater than 5, you're good. That's a quick way to check right there. Boom, done. We got it. We meet the expected cell count condition. We love it. We can get this other expected cell count right here. Let's go ahead and do it where we do row total times column total over grand total. I'm going to show you this one on the calculator right here. So my row total is 2,978 times 466 divided by 6,272. So this is 221.26, and that is our expected count right here. Now we need to do observed minus expected squared, that difference squared, over expected. So observed is 110. We observed that is the count, minus expected. Now we need to square this difference, so let's copy and times it by itself. It already does that for me. And now we need to divide by the expected. And we get a cell chi-squared of basically 0.2. So let's proceed. Adding up all those cell chi-squareds will get me the Pearson chi-squared test statistic right here. This is your chi-squared test statistic. We now need to know the degrees of freedom. Going back here, this is a 4 by 2. 4 by 2, 3 by 1. 3 degrees of freedom. There's your 3 right there. So this is a chi-squared with 3 degrees of freedom, and now we need to plot it. Let's go ahead and type it in right here. So the p-value is 0.2985. This p-value is very large. We have no evidence right here. You can also tell it visually right here. Just visually looking at it, it's nowhere near small enough. We would need 0.05 generally as our alpha, and below 0.05 to reject, and we're not going to have any sort of evidence right here because that is not a small enough p-value. Remember, according to the null, we should land at or around 0 because we expect the observed and expected to equal each other, the cell chi-squareds to be 0. Adding up all the cell chi-squareds gives you 0 because they did not deviate from the expecteds. So with this in mind, we didn't deviate enough to say there's enough of a difference. We have no evidence of a relationship right here. We would say that there's no association. They are independent of each other. I continue to believe the null. Here's what it looks like when we put it into a mosaic plot, and yeah, there's nothing going on here. You might say, oh, but look at the little difference. The boxes don't line up. And remember, that's what we used to do. Boxes don't line up. Well, they pretty much do line up. That's just little variations that we would see, and probably if we collected more data, it would get closer and everything would look better. Who knows? We do not know, but we do know right now that we do not have evidence. We do not have enough evidence to say that there is a relationship. And if you look at this, everything looks the same on the amount of people who get cancer, between the fish consumption. So we look across it, never small, medium, large. It doesn't really change. If you notice, it starts out a little bit higher, goes lower, because the yes right here. So there's a little bit more yes, a little less, a little less, a little bit more. But the changes are so small. It's just happenstance. It's just dumb luck. And this study doesn't prove anything. This study proves nothing. This study, they say, well, we started out believing that there was no association, and we still believe there's no association. This chapter right here is one that I love because I think if you practice it, you will get it down. It's, as you notice, the math process we have to go through. The first thing we have to do is we have to get the expecteds. We have to get the expecteds. The next thing we have to do is we have to get the cell chi-squareds. Then we need to find out which chi-squared distribution we're doing by the degrees of freedom. Then we need to plot our chi-squared test statistic and get the p-value. Then you make your decision. So once again, to review, I want to make it very clear. First, find your expected counts. Second, get your cell chi-squareds. Third, find out which distribution you're using. And fourth, plot your chi-squared value and get the p-value. Checking conditions should be in there too, but the math is what I'm more concerned about because conditions are just memorization. The math and the process is more important to me. So once again, make sure to practice the math. It never hurts to go over the conditions and just make sure you know them, but they are kind of memorization. And we see here our good old friends, randomization and 10% again. Good luck, and email me if you have any questions.